Okay, so welcome to the 38th video in the discrete structure series, and this video is going to be the start of a new chapter, counting and discrete probability. So under this topic, we'll be looking into different principles of counting, and under this, we'll be discussing the sum rule principle, the product rule principle, and we'll introduce this as the foundational concept in combinatorics. And combinatorics is the study of number of ways things can be combined. So the topics like permutations and combinations come into it. And then we'll introduce two more counting principles. One is called the subtraction rule. We have already studied this under sets in the inclusion exclusion principle. So the subtraction rule is the same as the inclusion exclusion principle. And we'll discuss one last derivative method of counting, and that is called drawing tree diagrams. And just to make you aware, we are covering this topic as part of the topic basics of counting. So I'm not exactly sure how deep we are supposed to go into this topic, but I am sure that we need to cover at least the sum and product rule principle as part of the syllabus. But I have seen some problems on this topic that make use of the subtraction rule. And there is also a relevant question that might involve drawing a tree diagram. So we're going to look into these two topics lightly and also exploring one problem of each just so we don't miss anything. Alright, with that said, let's get on to our first topic, and we'll be looking into the sum and product rule principles simultaneously. So let us describe both of these rules together. We'll find out some ideas about them and also learn where each of these rules apply. And then we'll be doing a few numerical problems on this topic. And in fact, let us start by stating these rules. So getting started with the product rule, and this has the following statement. Suppose that a procedure can be broken down into a sequence of two tasks. If there are n1 ways to do the first task, and for each of these ways of doing the first task, there are n2 ways of doing the second task, then there are n1 times n2 ways to do the procedure. Before getting into explanation, let us also quickly state the sum rule, that if a task can be done either in n1 ways or n2 ways, and none of the ways n1 is the same as n2, then there are a total of n1 plus n2 ways to do the task. Alright, so this looks pretty intimidating and complicated, but I can promise that things cannot get simpler than this. So these are really basic concepts. And I'll explain in an example, but this section should be relevant and you guys should be paying attention. The key part of this whole definition is this one. For each of the n1 ways, there are n2 ways to the second task. Okay? And if you go over to this side, this is the key statement, either of n1 or n2 ways. And to be honest, these rules are just abstractions. We can almost always tell by looking at the problem whether the product rule applies or the sum rule applies. So let me demonstrate with this example. Let's say I have a point A and another point B, and my goal is to travel from point A to B. And let's say there are three possible roads to go from A to B. So I'll draw the three roads. So that is the same as saying n1 is equals to 3, representing the three ways to go from A to B, or three ways of completing the task of going from A to B, just staying with this definition. And now we'll assume that over time, two more roads were built between A and B. So there are two more roads that got built, let's say after a certain amount of time. And I want to call these two ways as n2. And now if you ask the question, how many total ways are there to go from A to B? The answer is simply 3 plus 2 is equals to 5. So we can see that the sum rule applied in this case. And the key takeaway here is that n1 and n2 are ways of doing the same task, reaching from A to B. So in this case, we have n1 and n2 ways to do the task individually, and none of the three ways are the same as the two other ways. We have that here, none of the ways of n1 are the same as n2. So in this case, it says that we can simply add 3 and 2 and get 5 as the total number of ways to reach from A to B. I hope that is intuitive. And now let us look at this example. So let's say I have A and B, but this time I'm considering an intermediate point C that I want to travel to. Before getting to B, I want to go from A to C and then only reach B. And let's say there are three ways to go from A to C again. And similarly, we'll assume there are two ways to go from C to B. So I'll just call n2 is equals to 2, just like the previous example. And now if you want to count the number of distinct ways to reach B from A, we see that if I take this first road, once I reach C, I have two choices. I could go there and that will form one way of reaching B. And if I go from C to B via this road, that will form another way of reaching B. And again, had I chosen the second road to go from A to C, this one, that would give me another two possibilities, because now I could again branch over this road or this one. So have you been counting? We counted 4 till now. So choosing this and then that would give me two roads. And choosing this gives me two other possibilities. And same thing goes with the final road. If I choose to travel along this route from A to C, to go from this route to C to B, and from this route to B. And because of exactly this reason, for each of the n1 ways, all of the ways in n2 are repeating. Okay? In this case, each road from A to B is independent of any other road. To complete the task of traveling from A to B, we only need to choose one of these three or one of these two choices. But in this case, the second choice comes after the first choice. And to be precise, coming after is not the right term, but your ability to observe that both N1 and N2 must be chosen to complete this task. To reach from A to B, you have to choose one from N1 and one from N2. And like I said, the nature of the problem will be enough for you to decide which rule to use. And we have established that for these type of problems, the number of ways is given by the product N1 N2. And for these type of problems, the number of ways are given by N1 plus N2. Alright, with those basic ideas in mind, we'll dive into a few problems next. So a company rents a floor with 12 offices, but just 2 employees. How many ways are there to assign different offices to these employees? Okay, so starting with a basic question, we have a floor with 12 different offices and we only have 2 people to put into those 12 offices. And let's say these 2 people are A and B. So we approach this problem in this way. At the initial stage, all of the 12 offices are empty and A and B have both not been assigned to any office. So we'll start our job by first assigning A to one of the offices. And since there are 12 different offices, A could be assigned to any of those 12 offices. So the number of ways A could be assigned the office, given that he is assigned first, is going to be equal to 12. But once A gets assigned an office, there are only 11 remaining offices that can be assigned to B. And since these 12 possibilities correspond to A, there are 11 different possibilities for where B should be assigned. And now the big question, do we apply the sum rule or the product rule here? And for that we ask the same question as before. Does each of the 12 ways of A correspond to different ways of B? Like our first road problem? And you should be able to see that that is indeed the case. So if I pick any one of the 12 ways A could be assigned, all 11 ways for B will repeat because I'm choosing to put A in office number 1. And for this individual choice, B could be placed in any of the 11 offices. If I choose another office for B, office number 2, there are other remaining offices and each of those apply for this choice in A. So the nature of the problem is that for each choice in A, all of the choices in B are repeating. Therefore, we apply the product rule here. So let me do the solution first and I'll give an example to make it even more clear why the product rule is used. So the solution is pretty basic. We have already followed it here. We'll just mention the same thing. We'll say that the first employee can be assigned an office in 12 different ways. And then you mention in language, once the first employee has been assigned an office, there are 11 remaining offices. Therefore, the second employee can be assigned to any of these 11 remaining offices. So we'll just say that the second employee can be assigned in 11 ways. And now we just refer to the product rule. The total number of ways is given by the product of 12 and 11. And that is equal to 132. So this is the solution, pretty basic, but let us understand one more concept. So let's say in the same question, I did not have 2 employees, but just 1 employee. Okay, I only had A. And instead of a single floor, we'll assume that A alone is renting 2 floors. And each floor, let's say, has 12 offices. That means we have a total of 24 offices. And if we look into this problem, if we ask how many ways could A be assigned an office, we say that A could be assigned to any of the 2 floors. And each floor has 12 offices. So if I consider floor 1 and floor 2, floor 1 has 12 and floor 2 also has 12 offices. And in this case, the total number of ways we could assign an office to A is not 12 times 12, but this is 12 plus 12. So the sum rule applies here. And why do you think that is? See, assume that I assign A to one of these 12 offices from floor number 1. Then my job is immediately done. A has already been assigned and that's all I needed to do. It is not the case that for each way A could be assigned to one of these 12 offices, the ways to assign to other 12 offices repeat. It is not that case. But in this case, once I assigned A, all of the possibilities of B would repeat for that possibility of A. So this argument uses the sum rule and this argument uses the product rule. Alright, hope this analogy is clear. Let's move on to the next problem. Okay, we'll put this question on. The chairs of an auditorium are to be labeled with an uppercase English letter followed by a positive integer not exceeding 100. What is the largest number of chairs that can be labeled differently? Alright, so let us dive into this question. This question suggests that each chair uses a label. And according to the question, the label contains a single letter, let's say like B, and a number that does not exceed 100. So let's say 97 or any number from 1 to 100. And we are asking what is the total number of chairs that can be labeled distinctly in this way. So this is also just a very basic counting problem. We can see that each label has 2 components. one of the components is a single uppercase letter, and that could have 26 possibilities from A to Z. And for this numeric part over here, the question says that the number is going to be 1 of 1 to 100, okay? Not exceeding 100. So we have 100 different possibilities here. And the big question, do we add or multiply? Sum rule or product rule? So we can refer to the same train of thought as earlier. So if I were to fix it into a B, I can see that with B here, there are 100 different possibilities here. Because it could be anything from B1, B2, B3 up to B100. And if I choose a different character like C over here, all of the 100 possibilities repeat again for C. So we can recognize this as a type of problem that for each of the ways of 26, all of the ways of 100 are repeating. Therefore, we'll be applying the product rule. So we'll follow exactly the same answering technique. So we know that each level has an alphabet followed by a number from 1 to 100. And we'll get started with finding the total ways of choosing a single alphabet. And that is given by 26. And you could say because there are 26 distinct letters in the English alphabet. And then we'll say the total number of ways to choose the number following the alphabet. And this in my case is given by the question as 100. And therefore now we are free to apply the product rule. We have seen why using product rule. The total number of distinct labels is just equal to 100 times 26 is equal to 2600. And the number of distinct labels that we can create is the same as the largest number of chairs that can be labeled differently. Therefore, we can accommodate a maximum of 2600 chairs using this labeling paradigm. Alright, diving into more problems. How many different bit strings of length 7 are there? So we know that a bit string is just a string using zeros and ones. And I want to form such a string of length 7. So I'm going to have 7 characters or 7 bits. And each of these bits have 2 possibilities. They can either be a 0 or a 1. So that means there are 2 possibilities or 2 ways I could plug a value into this position. And the same argument would hold for all bits. We can put 2 possibilities for each of these positions. And now the job is to count the total possibilities, and the same question arises. Do we add these values or do we multiply them together? And again, if we think with the same chain of thought, let's say I fix the first digit as a 0. All of the remaining digits are allowed to repeat. So I do not know how many distinct ways there are to make arrangement in this range. Okay, so if I take 6 digits, let's say I do not know how many ways there are. And if I just assume there are W distinct ways, I can still argue that if I fix the first position as a 0, all of the W ways will apply. And if I change the 0 to a 1, all of the W ways will apply again. So if I know that for 6 digits, there are W ways, then for 7 digits, there are 2 times W ways. Because 0 and W gives one set of combinations, 1 used with W gives the other set of combinations. So it will just double the number of permutations that were in W. But then the same argument applies, right? If I fix this one, the remaining 5, whatever ways they can be changed in, this will just double it. So the core idea is that for each of these permutations, all of the permutations are allowed to vary. So this is exactly the criteria for the product rule. So we'll just be multiplying all of the 2's here. And what is our reasoning argument in our answer? So in the answer we say we want a bit string of length 7. And each of the 7 bits can be chosen in 2 ways. So we can apply the product rule. The total number of bit strings will simply be the product of 2 with itself 7 times, is equal to 2 raised to the power 7. And this will just be equal to 128. And we can verify that. Let's say I start counting with 7 zeros and I end my binary counting when I reach 7 ones. So between these 2 counts, all of the permutations of 0 and 1 will be covered exactly once. Because no 2 numbers are exactly the same, we already know that. And we also know from a little bit of binary work that this represents a 0 and this represents a 127. And we know none of these 2 numbers are exactly the same, right? Because if they are the same, they cannot be different numbers. So how many distinct numbers are here? If I had 1 to 127, I would have 127. I also have 0. So that is a total of 128, which is here. Yeah, so really basic questions and multiple ways to look at them. Alright, we'll look into one more type of question that involves counting functions. How many functions are there from a set of m elements to a set of n elements? Alright, so we need to count the number of possible functions between 2 given sets. So let me consider a set here with the m elements that is says, and then we consider another set B with n elements. So let me just show a few elements for demonstration. And we're going to count the number of functions from A to B. And there are a couple of requirements for a function that we know. Let's say this element is mapped to this element over here. Then we are not allowed to map the same input to another output. this link will not be allowed, assuming this link exists. And another rule that will disqualify this from being a function is if anything is left over here. If there is any element in A that is not mapped to anything in B, that is also not allowed. So for a mapping from A to be a function, we want each element not to go to two different elements because that would create an ambiguity. Therefore, we can lay our solution argument in this way. The number of functions from M to N corresponds to the number of choices, and that number of choices is M in the domain for each of the N elements in the codomain. Therefore, we can apply the product rule again. The total number of functions can be given by, and we need to repeat all possibilities M for each possibility of N. So we need to do N times N times N, M times. And this will be equal to N raised to the power M. So to make sense of this, let's say we have 3 elements here in M and 5 elements in N. So here we are saying we fix this element and we are saying choose any of the 5 that will be mapped from this one. Okay, so this could be mapped to this one, this could be mapped to this one, this one, this one, or this one. So for this first element, there are 5 different possibilities. And now for the second element, similarly, we are saying pick any of the outputs. So that gives me 5 more possibilities. And for the third element, I get 5 yet more possibilities. And this will be 125. But what happens if we do the other way around? Why is the answer not M raised to the power N? Because that would be similar to saying it in the opposite way. Choose one element of B and choose any one of those things that could map to B. Okay, so when I choose B, I could choose this as a mapping. And if I ask the same question for this element, choose any of these in order to map, I'm free to choose the same thing. I'm allowed to make this link according to the rule. And this will not be a function. So I cannot fix this and make you choose any of these. I have to fix one of these and make you choose one of these. Okay, so that is why N raised to the power M is the answer. Alright, so next we'll look into a couple of problems from the SOM rule. And to be honest, these will be questions of simple nature. The SOM rule doesn't have many complicated questions. So in this question, we'll say that a student can choose a computer project from one of 3 lists. The 3 lists contain 23, 15 and 19 possible projects respectively. And no project is on more than one list. How many possible projects are there to choose from? Okay, so very basic question. So there are 3 total lists. In the first list, there are 23 projects. In the second, there are 15. And in the third one, there are 19. And since no project is on more than one list, this means that these numbers do not have any intersections. And now, in order to find the total number of ways, this student could choose one of these projects. And again, the big question, do we multiply or do we add? I already mentioned SOM rule, so we'll be adding here, but I want you to be able to see the region. So once A chooses one of the projects from the first 23, these will not repeat. Okay, for the product rule, we want that for each choices, all other choices are valid and could repeat. But here, once I assign A to 23 or one of the 15 or one of the 19, I am immediately done. A has been assigned. And these ways, 23, 15 and 19 are the ways of doing the same thing, choosing one project. Okay, so in this case, we'll be applying the SOM rule. I'll not be mentioning any languages here, but the answer would simply be the sum of these 3 numbers. This is just equal to 57. Alright, next we'll tackle one a little bit complicated question. In the computer language BASIC, a variable name is a string of either 1 or 2 alphanumeric characters. And there are 2 more rules. A variable name must begin with a letter. So a variable name like A2 is valid, but something like 2A is not valid. It has to begin with a letter. And there's one more restriction. A variable name must be different from the 5 strings of the 2 characters that are reserved. And the question asks how many total variables are possible. Alright, so let's look into this. So the variable name either contains 1 character or 2 characters. But if it is 2 characters, it must begin with a letter. So must begin with a letter means that if you are using only 1 characters, it has to be a single letter. You cannot use a number because number cannot come first. And even if I use 2 characters, there are 5 specific strings that are reserved and I cannot use them. So for example, of could be a reserved keyword. So it has 2 characters and the word of is used in programming. So I cannot name a variable that is called of. And it says that there are 5 distinct strings like this that cannot be used as variable names. And before you point me wrong, I'm sure that of is not one of the 5 strings for the language BASIC. So please take this only for an example and for the concept. Alright, so we begin our solution in this way. Our variable either needs to have one character or two characters. So let's find v1. v1 is the number of variables of one character in length, and v2 is the number of variables formed with two characters. And then we know that the total number of variables by sum rule will be equal to v1 plus v2. How many one character variables are there and how many two character variables are there? The sum of that will be the total number of variables. So now we calculate the number of variables of one character length and two character lengths respectively. Now to find the value of v1, it's really easy because v1 is just using one character, and we know that for one character, since it must begin with a letter, the number of possibilities is just the letter, and that would be equal to 26 distinct possibilities from A to Z. And that is all for this case. So these will include variable names like a single A, single B, all the way up to a single Z. So these are 26 distinct variables. And now if we look into the possibilities of two characters, we know that the first character must begin with a letter. So the first character still has how many possibilities? It's gonna be 26 possibilities. And now if we look at the second character, how many possibilities are there? So here I need to put a letter, right? From A to Z. So that gave me 26 possibilities. But for the second character of the variable, I am free to choose a number as well as an alphabet. So I have 26 alphabets and 10 numbers. So that gives me 36 total possibilities for the second character. And therefore, if I need to calculate v2, I know that v2 will just be a product of these two possibilities. So it will just be 26 possibilities for the first place times the 36 possibilities of the second place. And this will just be equal to 936. And is that all? There is one more restriction. From these two character strings, 5 of them are reserved. So I calculated there would be a total of 936, but I'm not allowed to use all of them because 5 of them are reserved. So there could be something like this of, there are 5 total, things like that. So that means I cannot use those 5s. So let me just call this v2 total or something. And the actual number of characters that I'm allowed is just going to be equal to 936 minus 5. And this is going to give me 931. And now I can tell that the total number of ways is just going to be v1 plus v2. And this is going to be 26 plus 931. And this is going to give me 957. So this will be the total number of variables allowed in the programming language BASIC. So this question was kind of like a mixture. Let's see a couple of things. First, we applied a sum rule. We said that the number of total passwords would be the sum rule of v1 and v2. v1 was easy enough, but for v2, look at what we did. In order to calculate the possibilities, we applied a product rule, which are the possibilities of the first character, the second character, and then applied the product rule. But even inside the second character, we again applied a sum rule because there will be 26 possibilities for an alphabet and 10 possibilities for a numeric digit. So you can expect to get problems like this, which make use of both the sum and the product rules. And hopefully the goal is to be able to say which rule is going to apply in what situation just by looking at the problem. So if you are finding these steps really intuitive, you are in the right track. Alright, now we'll dive into two last questions for the day. And this question is going to come from the subtraction rule. Now we know that normally if there are n1 ways to do one thing and n2 ways to do one thing, we saw by the sum rule that I need to add them, n1 plus n2. And you know the criteria, n1 and r2 are the ways of doing the same thing, and none of the n1 ways are the same as the ways in n2. So that means there is no intersection between n1 and n2. But if there was an intersection between n1 and n2, this would not be enough. A union B is equals to A plus B. But only if there is no intersection. If there is an intersection between A and B, the formula would need to be adjusted and you need to subtract A intersection B. Okay? So whenever you are applying the sum rule, if you find that when you add, you are adding the same thing more than once because these things are not unique, then you'll need to subtract whatever common things were. And that gives birth to our subtraction rule. And we have already learned this as the Inclusion Exclusion Principle. So very basic, the name subtraction just comes from the fact that you need to subtract the intersection if the things that you are added have an intersection. So we'll look into a problem to make this concept even more clear. How many bit strings of length 8 either start with 1 or end with 2 zeros? So in this case, I'm looking for bit strings of length 8. So I want to first count all of the bits that start with a 1, no matter what these are. And in the next step, I'll count all of the bits that end with 2 zeros regardless of what these bits are. But at the end, when I have to merge these two possibilities, I'll realize that I have done duplicate counting. When I counted everything that started with 1, that also included a few things that had 2 zeros on the end. And when I counted everything that has 2 zeros on the end, I also counted a few things that started with a 1. Therefore, simply adding these two will not be enough. We'll also need to subtract out the common things that we counted in both cases. So let me show you the solution. So first, we find all bit strings that start with a 1. And we already know this. Once 1 has been fixed on the first place, there is no possibility of 0 here. That means I can only change the remaining 7 places. Yeah, and supposed to be 8 here. So we'll be only selecting these 7 places. And we know that there are 2 possibilities of 0 and 1 for each of these. So the number of ways will just be 2 times 2 times 2, 7 times. And how do we make an argument for that? So fixing 1 at the start, the remaining 7 positions has 2 raised to the power 7 possibilities. And this is just going to be equal to 128. Next we count everything that end with 2 zeros. So we do the same thing. We fix 2 zeros at the end, and that leaves us 6 different positions to play with. So fixing 2 zeros at the end, the remaining 6 positions has 2 raised to the power 6, and this is just be equal to 64 possibilities. And now can I simply add the 128 and 64? I cannot, because when I counted everything that started with 1, I also counted things that had 2 zeros on the end. And when I counted things that end with 2 zeros, I also included a few things that started with a 1. So there is an intersection between things that start with 1 and things that end with 2 zeros. So what is the number of that intersection? We want to find out that number of intersection and then subtract it later. So let's find out that first. So we'll say we need exactly those strings that start with 1 and at the same time end with 2 zeros. Because whatever the count of these is exactly the duplicates that I'm counting. Because these things are counted over here as well because they start with a 1, and these things are counted over here as well because they end with 2 zeros. So that is exactly the common thing that I want to cancel out later. And the way we calculate this is exactly the same as the first two. So we just fix 1 at the start and we fix 2 zeros at the end. And that is the same as fixing the 1 as well as 2 zeros here. That will only leave us the remaining 5 positions to play with. So we'll just say that the remaining 5 positions has 2 raised to the power 5 or 32 possibilities. So now what is the total number of possibilities and the solution to this problem? So we just say that we want to calculate the union of these two possibilities 1 and 2. And we know that this is equal to A plus B minus the intersection. So this should just be equal to 128 plus 64 minus 32. And this gives me a total of 160 possibilities. So this means there are exactly 160 strings that either start with a 1 or end with 2 zeros. Alright, we'll see one last problem for the day, and this involves using a tree diagram. And in this case, just diving into the question will be enough. How many bit strings of length 4 do not have 2 consecutive ones? So in this case, I want to find out all the bit strings of length 4 that do not have 2 consecutive ones. So if this is a 1, this cannot be a 1. And if this is a 1, both of these cannot be a 1 because that would make 2 consecutive ones. And there is obviously an analytical way to solve this problem. So we start by counting the cases exactly opposite to what the question says. It wants me to calculate things that do not have 2 consecutive ones together. So I could start by calculating all possibilities of having 2 consecutive ones together. I could also look for all possibilities of 3 consecutive ones together. And I could finally look for possibilities of 4 consecutive ones together. And if I add all of this, this will give me the number of possibilities where I can guarantee that at least 2 ones are together. And now if I take the total possibilities of all 4 bit strings and subtract this value, I'll get exactly the thing that I need, that they do not have consecutive ones. So that is the analytical way to solve the problem, but here we are looking at a tree diagram. So I'll even mention in the question, count using a tree. And to highlight a few concepts, counting using a tree is really easy, but it is not very scalable. If I have to count bit strings of length 8, for example, in the same question, it will be near impossible to construct a tree because the tree would be too large. But in this case, we can draw a tree and count this. Let me show you how. So we start by drawing a root node, and then all we do is to start exploring the possibilities for 0 and 1 until we reach our length of 4. So when I'm choosing my very first digit, I have 2 possibilities. I can choose a 0 or a 1. So if I happen to choose a 0, the resulting string that I'll get is just a 0. If I happen to choose a 1, I'll just get a 1. And now we'll simply continue down this tree while making sure that 2 consecutive ones do not occur. So here the last bit is a 0, so I'm free to choose both a 0 and a 1 because that will not cause 2 consecutive ones to be together. So if I choose 0, my string will become 0, 0. If I choose 1, my string will become 0, 1. But what are the possibilities in this case? So I cannot choose a 1 from here because that would give 1, 1 and that would make 2 consecutive 1s. So from this point, I'm only allowed to choose a 0 and that gives me one possibility, 1, 0. And what length have I reached yet? So these bits only have 2 characters. So I need to continue down 2 more steps. So what would you say are the possibilities here? Since the last character is a 0, I can choose both 0 and 1 while making sure nothing repeats. So if I choose a 0, I get 3 zeros. If I choose a 1, I get 0, 0, 1. And I hope you can see what happens here. Here, since I have a 1 at the end, I'm not allowed to choose a 1 because that will make 2 consecutive 1s appear together. So here I'm forced to choose just a 0 and that will give me 0, 1, 0. And what do you think here? Now I have a 0 at the end. I have 2 possibilities, 0 and 1. I'll get 1, 0, 0 here, 1, 0, 1 here. And with this iteration, I've reached the third level of my tree. Everything here is 3 characters, but I want to count things of length 4. So I'll go one more step. So in this case, this ends with a 0. So I have 2 possibilities, 0 and 1. That will give me 0, 0, 0, 0 and 0, 0, 0, 1. Okay. Now in this possibility, I have 1 at the end. So I cannot have another 1. I can only have a 0. So this will give me 0, 0, 1, 0. I hope you are able to follow this. And in this case, there will be 2 possibilities, both for 0 and 1. Give me 0, 1, 0, 0, 0, 1, 0, 1. What about here? 2 possibilities again. 1, 0, 0, 0 and 1, 0, 0, 1. This one is for 0 and for 1. And finally for this one, only one possibility, 1, 0, 1, 0. So when I've drawn this tree, I've effectively counted everything that my question needs. So the number of bit strings of length 4 is equal to the number of leaf nodes in this tree. 1, 2, 3, 4, 5, 6, 7 and 8. So you can just mention in language, the tree on the right shows all the possibilities that do not have 2 consecutive 1s. And we can simply count the leaf nodes. The total possibilities is just equal to 8. So this is all about counting using a tree. Really simple concept. And I hope you see why this is not very scalable. If I have to go 4 more depths beyond this, the tree will be really large and incomprehensible. But regardless, this is a valid way to count the possibilities of things. Alright, with that question and the segment, we are done for the video. The next video will be fully dedicated to the pigeonhole principle and the generalized pigeonhole principle. So I can't wait to see you guys in the next one. Have a good day and bye.